Okay, so this is the 53rd question of Zettili, second edition, second chapter. So in this particular question, we are given an operator A, that is x cap into d by dx plus 2, and we are asked to find the eigenfunction such that the eigenvalue of this operator A will be 0. And then we have to see if that particular eigenfunction is normalizable. Alright. And in the second part, we have to check if the A operator is Hermitian. And the last, we have to find 5 commutator relations for this particular operator and position and some with the derivative. So we will start with the first question, that is to find some eigenfunction. So let's say psi is that particular eigenfunction which gives us the 0 eigenvalue. So we can write it as A cap working on psi gives us 0 eigenvalue into psi. So let's put the value of A cap, that is x cap d by dx plus 2 into psi. Okay, we can actually remove this by, since it's all equal to 0, and let's separate this particular bracket, and we get d by dx of psi plus 2 psi equals to 0. Now d psi by dx equals to minus 2 psi. I'm moving this x over here, and just separation of variables, that is how we solve the ordinary differential equation. So we move the psi in the denominator on this side and this dx on the numerator here. So we get d psi by psi equals to minus 2 dx by x. Now integrating the both of the functions, we get ln psi equals to minus 2 ln x. Okay. At the moment, I have refrained from adding the constant term of the integration. So, and moving this minus 2 on the x, we get ln psi equals to ln 1 by x square. So we get the wave function as psi equals to 1 by x square. So this is our wave function, and now we have to see if this is a normalized wave function or not, and if not, then is there any way to normalize it. So moving on to the next part. Now to see that this function which we have got psi as 1 by x square, before we do that, there is one more thing. We can also add an ln c over here. This won't be much of a problem. This c will just come over here, that is c. So the psi will just be modified to c by x square, and to see if this psi is normalizable. Now there are two ways. One is by direct definition, that this psi should be finite, continuous, and its derivative should be also finite and continuous and single valued over the whole space. So by method 1, that is by definition, if we take at point at x equals to 0, we get psi equals to infinity. So psi is not finite. So from the definition we can say that this psi is not normalizable. Or method 2, we can go by integrating the probability density function, that is psi square dx from minus infinity to plus infinity. That gives us c square by x to the power 4 dx minus infinity to plus infinity c square. Okay, sorry. Just integrate that to c square minus 3 x to the power 3 minus infinity to plus infinity. And you can see that this is not finite value. If you can just go on and put the values of x as infinity, then you will that it is not a finite value that we will get. So once again we came to the conclusion that it's not normalizable. So with this we have completed our first question. Then we will move to the second part to see if the operator a cap is a Hermitian operator. So before we go on proving that this operator is Hermitian or not, there are two things I would like to mention first. That is, the Hermitian adjoint of x cap is nothing but x cap, and Hermitian adjoint of d by dx is minus d by dx. So this is Hermitian and this is anti-Hermitian operator. Okay, now coming back to our question to see if a cap is the Hermitian operator. To see a dagger is a. So let's start with our LHS, that is left hand side. We have a cap dagger equals to x d by dx plus 2 now the Hermitian operator can be distributed over the addition. So we have x d by dx of dagger plus 2 dagger. Now if you remember, the property of Hermitian adjoint is if there is, let's say, some p operator and q operator, and we apply a Hermitian adjoint on them, then we get Hermitian adjoint of q into Hermitian adjoint of p. Similarly, we use this over here, and then d by dx to x Hermitian adjoint plus the Hermitian adjoint of any scalar is, for a real scalar, is nothing but the number itself. Okay, now using this one, we put d minus d by dx, and using this we put x over here 2. Now what the final result of a dagger is minus d by dx x plus 2, which is no way equal to a cap. So operator a cap is not Hermitian operator. Alright, now we have to calculate the question C, that is asked to calculate certain commutators A a and x, a dy dx. So these are certain commutators that we are going to calculate. So I will not record every step of this, but I will certainly put the solution of this in the consecutive coming pages. First, let me explain at least one of them, and then for the rest of I will just put the solutions. So to calculate the commutator, we should a very good practice is to use a test function psi. Let's say we have a test function psi. Test function. So we apply this test function on the commutator. So expanding the commutator, we have a x cap minus x cap a cap. Okay, now put the values of a. So we have given a in the question as x cap d by dx plus 2. So this x is not, this capital X cap is nothing but the position. Okay, now we put the values of a. Or rather, first distribute this test function over the bracket, that is a cap x psi minus x a cap psi. Now x d by dx plus 2 into x psi minus x d by dx plus 2 into psi. So in the next step we get x d by dx x psi plus 2x psi minus x d by dx psi plus 2 psi. Now the differentiation of the products, that gives us x d by dx psi plus psi dx by dx plus 2 x psi minus x square d psi by dx plus 2x psi, and expanding this operator a bracket, we get x square d psi by dx plus x psi plus 2x psi minus x square d psi by dx plus, sorry, it should be minus over here, minus 2x psi. Now from here we can see that these two terms get cancelled, and also this one gets cancelled. So what we are left with is x psi. So we can say that, or let me write for the whole equation, a x psi gives us x psi. So comparing this, we can say that this two are equal. So a x cap is equal to x cap. The commutator of a x cap is equal to x cap. I hope this is clear. So for the rest, I'm thinking that should I put the solution or just leave that for you guys to work it on. So that's this calculating commutator is quite simple. Just take any test function and apply that on commutator and proceed with the normal algebra, and you will get the answer at the end. So we have to just compare the left and right hand side. So that's it.